So this talk, I'm hoping this is going to be an enjoyable talk. I usually my talks are focused on here are the features that are coming for the language, here's how to use them, etc. This talk is a little bit different. This is more about the internals of how is it that we implemented these features, what kind of bytecode is the compiler emitting, and how did we make some of the decisions that we made in the process of designing these language features. So in some sense, this talk is useless because none of you are writing Java compilers. On the other hand, I hope it's useful in terms of understanding more about how the machinery underneath the code you're writing works. So you've seen this slide before, nothing new, but you'll see it a lot. So this is going to be a highly technical talk. I hope at least some of you are familiar with what bytecode looks like, because I'm going to be showing a lot of bytecode. How many people here have written a compiler? All right, that's good. All right. How many people here have used Java P to dump the bytecode output of a Java class? All right, great. You're in the right room. Excellent. All right. So you shouldn't freak out if I show you some bytecode. I'm also going to talk a lot about the new VM facilities that were added in Java SE7, invokedynamic and MethodHandles, and how we're using those in Lambda as well. Okay, so brief introductory slide about Lambda. If you've seen my other talks this week, it'll be a repeat. I apologize for that. But the basic idea here is, if you haven't heard, if you've been under a rock, we're adding Lambda expressions to Java. Yay, finally, what took so long? So every language has its own little quirks, and so adding Lambda expressions to Java is slightly different from adding Lambda expressions to C# or Lambda expressions in functional languages, like Scheme or ML or Haskell. So we tried to respect the Java culture, and how Java libraries and Java code has been written, in the years leading up to Lambda, and that's influenced the design a little bit. So a Lambda expression is an anonymous method. Like a method, it has an argument list, it has a return type, a body, a set of thrown exceptions, etc. And the way we write them is you have the argument list. With or without explicit types. If you leave the types off, the compiler will infer them for you most of the time. An arrow, and then an expression or a set of statements in curly braces on the right side. In this particular example, this Lambda expression is a function that takes a person and what is names.add returns a Boolean, but we're treating it as if it returns void because the for each method expects a function from person to void. Like I said, very often elements of this can be inferred by the compiler. So the second example is identical to the first. It generates exactly the same bytecode. It's just that the compiler fills in some things for you. So in particular, it's filling in the type of the argument. And the way it does that is it looks at the signature for each. It says for each takes a interface that is isomorphic to a function from T to void. In this case, people is a collection of persons, so T is person, so E must be person. And furthermore, Lambda expressions can refer to names that are defined outside of their body. So this last example here, when I say people.removeAll, and I pass it a predicate, so that's a Lambda that takes a person and returns a Boolean, and the expression body uses this variable min_age, which you can see is not defined within the Lambda, so it must come from outside the Lambda. So that's capturing something from the local context. So these are the very quick tour of what Lambda expressions look like, and these concepts will of course come back when we talk about how we map this to bytecode. All right. Just a little bit of background about why we're doing this. There's a lot of reasons. The proximate cause is multi-core. That we want to be able to give people libraries that deal with parallelism for them because it's hard to do yourself. And in order to do that, there needs to be an easy way to take some behavior and say to a library, do this a million times. Do this for every element of a collection. Stripe this across a thread pool, you deal with it. You figure out how many threads. You figure out how to decompose it. I'm just telling you what to do. Parallel libraries need internal iteration. Internal iteration needs a code as data mechanism, and lambdas is that. That's obviously not the only reason why we would want to have lambda expressions in our language. It just happened to be the fire that was burning hottest under our feet at the moment that we started running. So lots of other reasons. You can write better libraries if you have lambdas. I gave a bunch of examples in my talk yesterday about libraries that you could write without lambdas, but that you wouldn't. And once you can, life is better. And also, there are other forces pushing us this way. We're kind of late to the party here. 10 years ago, it was kind of a radical idea to add closures to Java. Now it's what took you so long? Everyone else is there. We need to be there too. So we had a tool for doing some of these things before. We had inner classes. It was just too messy. It was clunky syntactically. It was clunky implementation-wise. It was... The rules for name resolution of what does a name mean, is it come from the lexical context or does it come from the superclass context? Very confusing. So they weren't good enough. They weren't doing the job. And so underlying the idea of let's add lambdas to Java, because we've sort of already we've taken that as a given that this is a good idea, there's still a big lurking question, which is, what does the runtime VM representation of a lambda look like? And that's really what this talk is about. So enough introduction, let's get to it. Okay, so the first question that you have to answer when you say, I want to add a new kind of expression to my language, is what is the type of that expression? Java is a typed language. So you have this new kind of expression. What's its type? In most languages, the type of a lambda expression is a function type. This is a structural type of function from T to U, function from int to int. Most languages that have lambdas started with lambdas from the beginning. They started with function types from the beginning. Their type system included structural types of, for any types T and U, function from T to U is also a type. These are also sometimes called algebraic data types. So Java doesn't have function types. So we could add them. That would be complicated. That's a possibility. Even if the language did, we also have to answer the question of what should the VM level representation be? And that's also a tricky one because the JVM has no native unerased way to represent a function from type A to type B. So in the VM type signature, since every time you call a method, you have to have the full type signature right there in the bytecode, we have to have a way of writing function from T to U so that the VM knows what the type of this thing is going to be, and we don't have a way to doing that. All right. Now, that doesn't, just because we don't have a way to do it now doesn't mean we can't add one, right? The language and VM specification, those are just documents. We can, open up FrameMaker and start editing them, right? So it's not that these things are impossible, but it does create a lot of questions. So some of the questions that we have to answer are, if we added functions, how would we represent them within VM type signatures? How do we create instances? What kind of bytecode do we execute to create an instance of a function? And how do we deal with this mismatch between the language type system and the VM type system? Not only does the VM erase generics, but the language also has to deal with variants. We have things like function from question super T to question extends U, which is a variant function. The VM doesn't have a way of representing that. So these are all challenges. And just as I said in my talk yesterday, given a choice between making language changes and making library changes, most of the time you want to pick library changes. They're easier, they're cheaper. If you make a mistake, you can undo it more easily. Well, the same thing applies with VM and language. If you have a choice between making a change in the compiler and making a change in the VM, you're generally better off making a change in the compiler. So we would like to avoid making significant VM changes if we can. So it's sort of all of these looming questions and all of the things that addressing them might have entailed that led us to a compromise with history. So we looked at how functions were represented in Java APIs up until now, and the way that we've always done this is to have objects that have one method and use that as our model for a function. So the Java class libraries are full of interfaces like runnable and callable and comparator and directory filter and things like that that are just holders for one method. And if you take the set of interfaces that have one method, this is isomorphic to the set of functions, right? The single method has a signature, it has an arity, it has a set of types, it has argument types, return types, and so we can treat this as a proxy for function. So rather than complicate the type system with a new kind of structural type, which would need a new syntax and a way to deal with erasure and lots and lots, we said, let's just keep doing what we were doing, and we'll take what we've been doing and we'll give it a name. Once you give things names, that makes them real, right? So we took this single method interface and we gave it a name. We called it a functional interface. And that answers our question, which is, what's the type of a Lambda expression? The type of a Lambda expression is a functional interface type. So here's an example of predicate. Predicate of t has a single method, takes a t, returns a Boolean. So you can think of function from t to Boolean. And the remove all method takes a predicate, and the compiler looks at this Lambda expression and says, okay, I'm expecting a predicate. That's a function from t to Boolean. I've got this function that has one argument. Okay, good so far. That one argument better be a t, and the body better evaluate to Boolean. And it does, and it's happy, and great. Okay, so the type of that Lambda expression in the context of this method call is predicate of t. So this introduces a new concept to the Java language, which it's not totally new, it's mostly new. We call target typing or poly expressions, where the type of an expression depends on the context around it. So we don't know the type of that Lambda expression until we know the types involved in the signature of remove all. And that's a little bit tricky because there might be more than one remove all method. We have overloading in Java. So the compiler has to do some gymnastics to figure out if there are multiple overloads, is one better than another? And if it can't figure it out, it just reports an ambiguity. Otherwise, it says, oh, that must be the method you mean. Therefore, these must be the types you mean. And I'm going to call this Lambda a predicate of person. So that's great. Compiler does all that work for us. The Lambda converts to predicate of person. But we haven't really answered the question yet, which is, okay, what happens? What code is the compiler going to generate? How do we go from that thing to an instance of predicate of person? So there's an obvious answer. Why not just use inner classes? We have inner classes. We understand how they work. We could say that a Lambda is just an inner class. And there were a number of people who advocated this as an approach for how to implement Lambdas in Java, is just to say Lambdas are just a better syntax for inner classes. The plus side of that argument is it's dirt simple. We're building on something that already works. We could be done in 5 minutes and go home. The downside of that is we got into this exercise because there were some things that were wrong with inner classes. And why would we want to build the future on the flawed past? So if we chose to take this strategy, and you've already figured out we haven't, right? But bear with me, pretend we chose to take this strategy. What the compiler would do when it comes across a Lambda like this one, which takes a person and whose body is, invoke the getAge method on that person and then compare it to this minAge variable that's captured from outside the Lambda, that would map to an inner class that looks something like this one, where we have a class, anonymous, generate a name, foo$1, implements predicate of person. It has a captured argument, which is stored in a field and passed to the constructor, and then the body calls the getAge method, typo there should be some parentheses here, and compares it to the captured variable. Right, so this is what the compiler generates today if you capture an inner class. And so we could have just done that. Upside, done in 5 minutes, can go home. Downside, well, many of them, including the fact that we're still stuck with one static class in your application in the file system, per Lambda expression in your code. And how many people here find it annoying just how many class files inner classes generate when you build an application? All right. Now, given that inner classes are already annoying to use, so we avoid doing it, if we make it less annoying, would we get more of them or less of them? Right? So we have a situation now that we're sort of like barely willing to tolerate, but we don't want to make that situation worse. Okay. So if we were to translate lambdas to inner classes, the capture would be really simple. Right? So the compiler would see code that looks like this, and it would generate code that says, just call the foo$1 constructor, take the captured variable min_age, pass that to the constructor, and that's what the compiler emits. Well, that wouldn't be so bad. And the bytecode for that is pretty straightforward. I'll walk through it quickly. Push the list on the stack. Create a new foo instance, pass min_age to it, invoke the constructor for that, and then pass that to the remove_all method. Pretty straightforward. So that, again, done in 5 minutes, go home. The downside, as I said, if we translate it to inner classes, we would be inheriting most of the problems of inner classes. There's the performance issues of you have static classes that have to be stored in the file system and loaded and parsed, and we have a lot of classes that implement the same interface. So if we have 100 classes that implement runnable, any call site that invokes a runnable now has what we call type profile pollution. The VM says, well, I don't know what type I'm going to see here. I've already seen 112 of them. So I'm just going to have to fall back to a full virtual dispatch instead of being able to do inlining or inline caching or what have you. So having a lot of instances of runnable pollutes our type profiles at runtime. There are also complexities for the user. The complicated name lookup would be then inherited by Lambda expressions, and all the mistakes we make with inner classes we would be making with Lambda expressions. So that's all bad, but that's not the worst of it. The worst of it is the fact that whatever bytecode the first Lambda-enabled version of the Java compiler emits is the binary interface for what a Lambda looks like from now until the heat death of the universe. So we don't want to just emit some code, see if it works, and then emit different code. We don't have that option. Scala has that option. We don't have that option. So we have to be prepared to make a commitment for the end of time, for better or worse, in sickness and in health, blah, 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 of how we want to represent Lambdas, not only in the type system, not only in the language, but the binary representation in class files. So whatever we do, we're stuck with it forever. And there's something really yucky about picking inner classes as your binary representation. You're conflating a particular implementation with the canonical representation. It would be nice to just have a canonical representation for a Lambda and not be stuck with having it be tied to one implementation. Okay, so a little bit of bytecode background. So up until Java SE7, there were 4 bytecodes for method invocation: invoke static, invoke virtual, invoke interface, and invoke special. The first 3 are pretty obvious. Static is for static methods, virtual is for class methods, interface is for interface methods, and then invoke special is the garbage can for everything else, right? So constructors, supercalls, private methods, all the weird stuff that doesn't fit into one of the first 3 buckets gets thrown into the invoke special bucket. What's common across those is they each specify as a target a class name, a method name, and a method signature. And we saw 2 examples of that in the bytecode I showed you for inner classes. There was an invoke special that we used for the constructor, and there was an invoke interface that was used to call the remove_all method. So you see, we name the class, we name the method, and we name the full signature with all the static types of all the arguments and the return type. Okay. Well, that will become relevant later. Okay, so if we look at the tools that we have for representing things in bytecode, Java SE7 gives us a new tool, MethodHandles. Okay, so this is a VM level representation for something that if you squint kind of looks like a closure. Okay, maybe we could use that. One of the things that's useful about this is that you can store these things in the constant pool. And then just in the bytecode, you can use load constant bytecode to just load up and say, get me a method handle for this method. And it's a constant load. It's very fast. Okay. You can also reflectively, well, not reflectively, but reflective-like mechanism to say, look up this method and give me a method handle for it. And the nice thing about it is because the VM understands what it is, the VM can happily inline through these things. And the API for method handles contains ways of slicing and dicing them to like insert arguments and remove arguments and adapt the arguments to box them or unbox them and compose methods. You can think of it as the compiler writer's Swiss Army knife. So this seems like an attractive way to represent lambdas. So let's give that one a try. So, after we've eliminated the first obvious choice, let's look at the next obvious choice. Lambda is a language-level method object. A method handle is a VM-level method object. So why not desugar Lambda bodies to methods and represent lambdas as a method handle for that method? Seems simple, right? All right, you're not falling for it. Okay, so if we were to do this, the code would look something like this. We have this lambda that we want to pass to remove all. We've desugared it to a method. Let's call it lambda $1. And so in order to make the call, we'd generate an LDC bytecode that says load this method handle constant out of the constant pool. And now we have to insert an extra argument into it to represent the capture of the min-age argument. So we use the combinator that says, take the method handle, give me a new method handle with this argument inserted at the beginning of the old method handle's argument list, and pass that to remove all. And the desugared method looks something like this here, where I have the arguments that are part of the functional interface type, plus an extra argument for the captured value. So, okay, this one's not so hard. We might not be home in 5 minutes, but we might be home, for dinner. So, what's the downside? Well, think about what the VM signature would look like. If we did this, the signature of list.removeAll would just have method handle in it. So, what's one of the bad things about erasure and generics? You can't overload list of integer with list of string. Well, this is even worse. You couldn't overload any two methods that took lambdas. So, this is, super mutant erasure on steroids, right? So if that's bad, this would be worse. We don't want to do that. So that's unfortunate. It would have been nice if we could have used this trick, because from a runtime perspective, it would be really nice. And again, this is picking an implementation and burning it into bytecode. Okay, so let's take a step back and think about what we've tried two paths. We've bumped our head on both paths. Ideally, what we want is another layer of indirection. We would like a binary representation that isn't tied to a specific implementation strategy. We certainly don't want to tie to inner classes because they stink. Tying to method handles is just too low level. And we don't, not only don't we want to change our representation, we don't want to force users to recompile their code just to get a different implementation. That's not how we do it in Java. Once the user compiles to a class file, we want that class file to be good forever. And if there are things that we want to change, well, we change those in the VM. So, the answer to any hard problem in computer science is another layer of indirection, so that's what we want. We want to be able to have the static compiler emit not code to create a lambda, but a description of what a lambda is, and let the VM create it. So we put the recipe in the bytecode, the runtime executes the recipe the best way it knows how at that time, which could change from version to version, and hopefully we want it to be really, really fast. So in addition to adding method handles to Java in Java 7, we also added another bytecode tool, invokedynamic. So this is added to the other 4 invocation modes: static, virtual, interface, and special. InvokedYnamic, or Indy, we like to call it. And the idea is the other invocation modes, their semantics are very tightly tied to the Java semantics. You know, the semantics of InvokedDynamic are designed to be pluggable. And the idea is when you have an InvokedDynamic call site, in addition to all the things you have at a regular call site, you know, a method name, a method argument, you know, list, etc., is you have a pointer to what's called a bootstrap method. A good way to think about the bootstrap method is it's pluggable semantics. It's language-specific logic. And the idea is the VM wants to consult the language logic to say, I have a call site, I don't know how to link it, help me. Have the language logic come in and say, okay, well, you know, the semantics for Ruby would be, you would do this, and tells the VM the answer, and then the language logic gets out of the way, because we don't want to vector through that logic every time we make a call, otherwise it'll be dog slow. So the idea is the VM and the language become partners in call site linkage in such a way that the VM can ask the language, what would you do here? And under what conditions might you do something different? So the VM knows it doesn't have to keep asking, what would you do here, what would you do here? And as an example, so you know, imagine you have a dynamically typed language, and you have a method add AB whose body is A plus B. Well, we don't know what the types of A and B are, but let's assume that this language has more than one numeric type. It has integers and floats. So I could call add with 2 ints, 2 floats, an int and a float and an int. So in the pessimistic approach would be every time through this call, I'd have to look at the types and say, what body of add do I call when I have an int and a float? In the real world, if I call this with 2 ints, the next time I call it, pretty likely to be calling it again with 2 ints. Because maybe I'm in a loop, right? And I'm doing the same thing. So I don't want to have to do that dispatch logic every time someone calls add. I want to be able to say, all right, I've been called with 2 ints. Here's the target for adding 2 ints. And if the types are the same next time, call that same target next time. And if the types are different, okay, ask me again. All right? So InvokedDynamic has this mechanism for the VM and the language runtime to have this conversation about how often and for how long the language runtime has to be involved in linkage decisions. So even though these types could change from call to call, they don't change that often, and the big win is not having to relink the call site for every call. Then the VM can inline through it as long as the assumptions aren't violated. Okay, so what happens is the first time you stumble across an InvokedDynamic call site, the VM calls the bootstrap method. It returns a data structure that represents a linked call site. And inside that call site is not only what method handle do you execute when you have to call this, when you invoke this call site, but under what conditions would you need to relink this call site? And in the absence of saying that it has to be relinked, the VM doesn't consult the bootstrap ever again. Okay, and then the VM can inline through these call sites. Okay, so what's in the bytecode for an Indy is a little bit more complicated than what's in the bytecode for the other invocation modes. In addition to the things that we had before, which was an argument list, a method name, and a signature, there's this pointer to the bootstrap method, which you can think of as the language logic, and also a static argument list, which is known to the bootstrap, which has information that is statically known that can help in the linkage decision, and why this is important will become clear in a few moments. So, at this point, you may be wondering, why am I talking about InvokedDynamic? Java's not a dynamic language, right? Who's thinking that? Oh, come on. All right, thank you. Okay, so Java is not a dynamically typed language. But Java is an extremely dynamic language. It's a dynamically compiled language. So the dynamism here is not what is the type of this parameter, because that's static. But the dynamism here is what code do I want to generate when I capture this Lambda expression. And we've already talked about two possible code generation strategies: generate an inner class, convert to a method handle. There's other things we could do. We could use dynamic proxies, although why would we want to? We could use some VM private APIs for constructing objects out of raw bits in Alchemy, right? There's lots of ways that we could generate code for lambdas. We would like to be able to make that choice dynamically and have that be a pure VM implementation detail. And that's what Indy lets us do in this case. So we have a binary representation, which is the specific invoke dynamic argument list and bootstrap combination that we're using. And that's our Lambda recipe. And then all the implementation details are in the implementation of the bootstrap, which can use different code generation strategies for different days of the week. So the recipe for constructing a Lambda has to include a bunch of things. If we desugar the Lambda body to a method, we have to include a reference to that method. So that'll be a method handle for the implementation. We also need to name what functional interface are we converting to. So if we're converting to predicate, we have to somewhere the predicate.class has to appear in the argument list. And if there are values that have been captured by the Lambda, those have to show up somewhere at the Lambda capture site as well. And then there might be some additional metadata that the compiler knows about that it needs to capture, like should this Lambda be serializable or things like that. So what we do here is when we want to capture a Lambda, the compiler generates an invoke dynamic, and we call that call site the Lambda factory, because you call this call site and it returns the Lambda that you want. And it's invoked with invoke dynamic, and it returns an instance of the selected functional interface. And the second time I call it, it's much faster because it's already done the linkage and we've bypassed the slow bootstrap path. So, okay, so what does this look like? The first thing we do is we desugar our Lambda to a method. We derive the signature of this desugared method from the signature of the functional interface. If there's any extra arguments that are captured, we prepend them to the argument list. So for this Lambda here, where we capture the variable k, we have an extra argument for the captured k. If the Lambda doesn't capture the instance at all, it doesn't reference fields, it doesn't call super or anything like that, we can desugar to a static method. If it captures the instance, we can desugar to an instance method. So this is what the compiler does. And then when we want to capture the Lambda, this is how we translate it. I've used a sort of pseudo notation for representing an invoke dynamic call because we don't have syntax in Java for making an invoke dynamic call. The bootstrap method, the language logic for this invoke dynamic site is part of the Java language runtime. It's in java.lang somewhere. And it captures the translation strategy. That's just part of the runtime implementation. We call this bootstrap the metafactory because it's what creates the factory. What we do is we do an invoke dynamic. We say our bootstrap is the Lambda metafactory. This is part of the language runtime. The static arguments are the things that are known statically to the compiler, where the target type is predicate, and the desugared Lambda body is this Lambda $1. And then the dynamic arguments to the invoke dynamic instruction here are the captured arguments, the things that we would have passed to the inner class constructor. And the result of that is going to be an instance of predicate, and we just pass that to remove all. Okay, so this is the code that the static compiler generates when you capture a Lambda. Okay, if you do Java P, you'll see it'll dump out the bootstrap method table, and you'll be able to see the structure of it. So anything that's known statically goes in the constant pool. What am I converting to? What's my behavior? And then anything that's only known dynamically, like the captured arguments, those go in the standard dynamic argument list. Okay, so how do we get bytecode out of this? Right now, all we have is a description, and we have some invoke dynamic bootstrap that's expected to take this description and turn it into an object that implements the appropriate functionality. So we spin bytecode at runtime. This is easy. We use ASM. It's not hard. So the simple strategy is, well, spin the same inner class that the compiler would have generated, but spin it dynamically at runtime. So that's a simple strategy. That might be our V1 strategy. And then once we spin that class, we tell invokedynamic to link the call site to the constructor for that new class. And it just so happens that the shape of the dynamic argument list and the shape of the constructor argument list are exactly the same. They're the captured arguments. So that's one way we could implement it. We have this implemented. It actually works pretty well. There are other ways we could implement it that might be better that we're experimenting with. Another way we could do this is spin one wrapper class per functional interface type. So one wrapper class for runnable, one wrapper class for comparator, etc. And have the constructor of this synthetic class take a method handle. And we pass the behavior method handle to the to the constructor of this class, and it binds the behavior to those methods. Like I said, there's other tricks we could do. We could do dynamic proxies. We could use method handle proxy. We could use VM private APIs, etc. The good news here is we don't have to pick a strategy until runtime. Our VM could use a different strategy from IBM's VM. We could use a different strategy for embedded as we do on a server. We can use a different strategy on Tuesdays if we wanted to. Okay? And this gives us a lot of flexibility. Okay, so let's talk about what invokedynamic gives us, because there's all of these benefits that have nothing to do with dynamic typing. So one of the cool things is invokedynamic is the ultimate lazy initialization idiom. So think about the common case. You've got a lambda that doesn't capture anything. You know, A comma B maps to A plus B. It's not capturing any variables from the lexical context. So how many instances of this lambda do I ever have to make? One, right? When we do this with inner classes, we all do it manually. We say, you know, private static final comparator C equals, and we do it by hand. Well, the VM can do that for you. The VM can look at this and say, this is a non-capturing lambda. It could tell it's non-capturing by the dynamic argument list to invokedynamic being empty. And say, okay, the first time we call the bootstrap, I'll make one instance. And then I'll tell the VM to link this call site to be always return this constant. And the VM optimizes that into a constant load, so the call goes away. So this is a very common case. A lot of lambdas capture nothing. Probably 50% or more capture nothing. So instead of having to do this by hand in the source code, we just let the VM do this for us. And in that case, invokedynamic functions as a lazily initialized cache, which is cool because if we never use the lambda, the overhead is 0. There's no extra fields for the static initializer. There's no static initializer to run. And once you create one, stateless lambdas get lazy initialization and caching absolutely for free, and the cost of capture goes to 0, and I mean 0. So that's a cool benefit. What else does Indy give us? It also gives us an opportunity to procrastinate, and procrastination is good. We defer the choice of code generation until runtime. That makes it a pure implementation detail. We can change it dynamically from run to run, from minute to minute. We can pick our binary protocol now and pick our implementation later. So effectively what we're doing is we're moving some of the complexity and some of the implementation choices from the static compiler to the VM. And the VM always makes better decisions than the static compiler because the VM has more information with which to make those decisions. So the more hard decisions we can move to the VM, the better performance we're going to get. I'm surprised Marcus is not arguing. Are you here, Marcus? Yeah, I figured you'd be arguing by now. Okay, so... Okay, good. So this gives us a chance to change our code generation strategy dynamically. All right, so the other thing Indy gives us here is it gives us an extra level of indirection for no extra level of cost. So that's really nice, because, and the reason there's no extra level of cost is once you link the call site, the bootstrap gets out of the way. So we deferred our code generation strategy to runtime. We're only paying the price once. So for example, let's say we pick the strategy of spinning an inner class. So the first time you capture the Lambda, yes, we're going to pay this cost of using ASM to spin a class, and we write it into an array of bytes, and then we call the class loader and say, load me a class. That sounds like a lot of work. It's actually not any more work than go out to the disk, scrape the bytes off the disk, and then load the class. Most of the work is in loading the class. So we're still loading a class. We're just loading one that we generated in memory. We did some work to generate it in memory instead of going out to disk and loading it from there. Once we pay that cost, subsequent captures are free. In the non-capturing case, it gets optimized down to a constant load. And in the capturing cost, the subsequent cost is invoking the constructor of this synthetic class, which is no different from what we would have done before with inner classes. So the worst case is exactly as bad as the previous worst case. The best case, much better than the previous worst case. So that's winning. So invokedynamic gave us this opportunity to have an extra level of indirection between our code and our code generation strategy without paying a cost for it, except for that one-time startup cost. Okay, so you're probably wondering, how much does this cost? I have some numbers. Any translation strategy we pick is going to impose costs at a couple of layers. There's the one-time capture cost, the linkage cost. There's the every time through capture cost. What does it cost to make a new Lambda? And there's the invocation cost. What does it cost to invoke the Lambda method? So I have numbers for one of these. I don't have numbers for all these right now. But if you compare this to the way we did it with inner classes, the one-time cost is linkage and class loading. The capture cost is invoking the constructor. And the invocation cost is an invoke interface. So we had our performance team run some numbers. So they ran it on a big honking server, 80 weight, and a Halem EX server. All of these numbers are in operations per microsecond. So there's 3 columns. The first column is performance just running single-threaded. The second column is performance keeping all the cores busy. And the last column is just the ratio of the two. And the rows are doing a regular inner class, capturing a Lambda that doesn't capture anything from the context, and capturing a Lambda that does capture something from the lexical context. So you'll notice that the capturing Lambda cost is exactly the same as the inner class cost, because we're linking the call site to an inner class, dynamically spun inner class constructor. The non-capturing cost is about 4 times better. So that's a win. If we move over to the multi-threaded case, the non-capturing Lambda cost is almost 20 times better. And that's because we're not doing any allocation. We don't have any contention for the heap, etc. So we have strictly better performance, and we have better scalability in the happy case. And the happy case is really common, right? The happy case is like at least half the time, and the unhappy case is exactly as bad as it was before. So this is a pretty darn good trade-off. Okay, so this is cool. It's a cool trick. We can implement this trick in the JDK, and not only the Java language can use it, but other languages that run on the JVM can use it as well. So what we've basically added to the platform runtime is a mechanism to say, take a method and convert it to an instance of a functional interface, which is great because if you're writing the compiler for, say, Jython, you're probably going to call methods on collections. The methods on collections are expecting functional interfaces. You have a choice between generate your own classes or let the VM do it for you. Which do you pick? Right? So this is a mechanism that's not just useful for the Java compiler. Anybody generating code that's targeted at the JVM will probably find this useful and make their generated code smaller. And then if we make this faster later, you get the benefit of that for free. Whereas if you generated your own bytecode, it would be exactly as fast as it is now. So this is a win not just for the Java language. It's a win for language-to-language interop. Or language to Java interop, anyway. Okay, so could we make this better in the future? One of the things that we're looking at is having the VM intrinsify Lambda capture sites. Okay, if the VM recognizes the bootstrap and says, "Oh, that's a Lambda capture," Well, it just happens accidentally that the lambda capture semantics map directly to MethodHandle algebra semantics. Nice coincidence. So since the VM already knows a lot about combining method handles, it can say, oh, I know what that invoke dynamic is doing. It's taking that method handle and convolving it with these parameters, and I know that that's a side effect free operation, so I can do code motion optimization on it, and I can do escape analysis optimization on it. And you can think of this lambda conversion as a boxing operation. And if the compiler is free to do code motion on it, if it can move it, the box, to where it's right next to the unbox, it can eliminate it outright. And optimize away all the capture overhead. So this won't be innate, but we're working on it. There's a lot we can do. And so a lot of standard compiler optimization tricks, escape analysis, code motion, box elimination, can be brought to bear on optimizing lambda capture. Okay, so this is all exciting, right? Good news? In a good mood? All right, so let me talk about something that's going to dampen your good mood, which is serialization. Okay, serialization is unquestionably the worst language feature ever added to any language that made it out of the nursery. I'm sure there are worse language features added to languages, that just, died at birth. But, this is the worst language feature that ever made it to users. And it's the gift that keeps on giving. So I would say fully 30% of the effort, of the Lambda effort, has gone into, oh my God, what are we going to do about serialization? And we're not done with that. So everyone's first reaction, which is good reaction, is, can we just ignore it? Well, we can't really ignore it because let's say I have a functional interface foo, it extends serializable, and some user comes along and says foo f equals, and then gives it a trivial lambda. They expect that to serialize, and that's not unreasonable, right? If this thing were to be not serializable, they would rightfully complain that we lied to them. Because, the interface is serializable, there's nothing remotely non-serializable going on here. Why wouldn't this work? So, okay, we have to make this work. Okay, well, so this is where our very clever dynamic translation strategy turns around and bites us on the backside. Because if we were just doing the inner class thing and had gone home at 9:05 this morning, we could just serialize the object and be done because there would be an actual class with a name, foo$1, that we could serialize. But there is no class. Whatever the representation of this lambda at runtime is something that we just made up out of raw bits and is not guaranteed to be there on the other side. It's not going to have the same name on the other side. So the implementing class won't exist at deserialization time. So I guess we could serialize it. We just couldn't deserialize it. So that's kind of rude. So we won't do that. Worse, let's say the thing did have a name. Well, let's say we serialize it on RVM and we deserialize it on a different version of RVM, or we deserialize it on IBM's VM. Maybe that other VM is using a different translation strategy. So we, even if we could serialize the class, we wouldn't want to do that. So what we really have to do, we had a dynamic code generation strategy. We need a dynamic serialization strategy. We need to reconstitute the recipe for the Lambda, serialize that. And without introducing any new security holes, right? Because Lambdas are private methods, so we're ultimately going to need a way to call that private method, but we don't want to hand users a mechanism to call any private method that they happen to put in a maliciously constructed bytecode stream. So, okay, tricky problem. So, serialization gives us a couple of tools for this. There's the read, resolve, write, replace methods, which allow you to intercept serialization and deserialization so that when you go to serialize a Lambda, you can implement this write, replace method, which says, don't serialize that, serialize this instead. So what write, replace does is creates an instance of, Lambda recipe or something like that, that has all the nominal components that were present at the invokedynamic capture site, and serializes that. That means that the metafactory has to provide a way to get at that information at serialization time, which imposes some extra runtime cost on serializable lambdas. So what we do is we actually have two metafactories, one for the fast path and one for the horrible path. And that way, all the cool VM optimization tricks can apply that I talked about can apply to the fast path, and well, serialization users get what they deserve. So on deserialization, now you have a recipe. You have to turn it back into a lambda, and with whatever strategy for code generation you're using at that day of the week. And again, we have to verify that this lambda recipe was a legitimate recipe and not a maliciously constructed recipe. And the way we do that is we include in the serialized form what class captured the lambda. And then we hand the recipe back to that class and say, is this one of yours? Do all the fields, the class name, the method name, the signature, the captured argument list, etc., match exactly some lambda that you captured? And if so, we let it reconstruct it. And so it's kind of one of these security Aikido things where, you have this maliciously constructed thing, you hand it back to the guy who supposedly created it, and we said, all right, we'll let you tell me if this is one of your children or not. So it's actually a pretty cool trick. There's a paper on this on the Project Lambda website. If you go to openjdk.java.net/lambda, there's a paper on the translation strategy that has much more detail on the serialization if you're masochistic enough to be interested. Okay, so wrapping up, we use invokedynamic to capture lambda expressions, not to give us dynamic typing, but to give us flexibility in choosing a translation strategy and good performance for that. Even using the dumb strategy, which is spin an inner class at runtime, it's either no worse than or much better than inner classes, so we're better out of the box. And it leaves a lot of running room to come up with better implementation strategy in the future without breaking compatibility. So some places to go for more information. That's the URL I was just mentioning. The Project Lambda page on OpenJDK has all kinds of documents. And if you're interested in binary builds, you want to try this out, you can download them from this bottom URL here. And with that, I'd be happy to take questions. Yeah?
How are you handling the problem of megamorphic?
So I'm not handling the problem of megamorphic. That's the VM's job, right? So I'm generating bytecode. I'm trying to generate the best bytecode I can. Is
the VM planning on handling? Because it seems like Lambda is going to encourage a programming style which is going to be hostile to inlining.
So just a second. So folks, you're welcome to leave, but if you could do so quietly so the people asking questions can still hear. Yes, all right, so the question is, this seems like it's going to encourage a style where I'm going to have a lot more megamorphic call sites. We're doing some things, like one of the alternate translation strategies that I suggested reduces the breadth of the type profile at call sites. So I'm not sure it's strictly worse for that. It's a problem we're going to have to deal with, but it's really orthogonal to what we're doing here. I don't have a good answer for it, otherwise I'd give you a better answer. Sure.
Can there not be a kind of a mismatch between, so if you serialize your lambda that has captured some outer state,
yeah,
and it reconstitutes itself somewhere else in a context where it's like, okay, that's fine, these could be my children, like you said, but they're kind of at this moment in another state because the dynamic arguments have been filled in from there. And so what is this not going to happen?
So the question is, what happens to the captured arguments when you serialize? So we serialize those too. So if you capture arguments, we serialize them. They better be serializable. Same rule for inner classes, right? Any argument captured, for a serializable inner class has to be serializable, and then they just get reconstituted at the other side.
Yeah, okay.
Okay, yeah. Come back to me when you have that. So more questions? Yes, over here.
You were talking about invokedynamic reeling. How, depending on argument types, how does
So so first of all, the way that we use invokedynamic, the call site's only ever linked once. We never we always say here's the target. It's never going to change. That's sort of a separate question. How do we deal with generics is a good question. So what we do is we spin a class. We're handed some information about what functional interface that class has to implement. And when we spin it, we have to spin bridge methods for all of the bridge methods that the compiler would have generated if this was a statically compiled class. And so if you have a method that's, whose argument takes a t, right, so you have add of t, what it does is if you have a subclass where t is string, the compiler generates an add of string method and an add of object method. And then the add of object method is what's called a bridge method. It just invokes the add of string method with a cast. So we do exactly the same thing. We generate methods for all the bridges. Any other questions? In the back. Yeah, stand up. It might be easier. So the question is, I serialize an object on one VM, I deserialize it on another VM, right? So whatever VM I deserialize to needs to have a language runtime that knows about lambdas, because the serialized object is going to be an instance of, lambda recipe or something like that. So that wouldn't, if you tried to deserialize it on a 6 VM, you'd lose. But if you tried to deserialize it on, say, IBM's, Java 8 VM, it would know how to interpret the serialized lambda object as a recipe and then feed it into whatever mechanism it's using for constructing lambda instances. So you create a lambda instance and then you call getClass on it and you try to do reflection on it. Is that your question? Yeah, so those methods will exist, right? Because what will happen is once I convert the lambda to an object, it's an object. The object has a class. The class is some subtype of predicate or runnable or what have you. So if I say get method on it, I will get all of the methods that were generated into that object, and I can invoke them reflectively, no problem. The class name might be something I don't recognize. It might be lambda $22, but that's fine. Yeah, I don't think it will. I don't think it'll break things like that. I mean, it's. Yeah, I hope no. Well, so I certainly hope that people are trying this out, and if it's not working for you, let us know. I mean, like I said, we have binaries you can download, and it would be. I mean, the single most valuable thing that people can do for us in OpenJDK is download the code and try it on your code. And then just come back and say, yay, it worked, or oh, it didn't work. Here's what I was trying to do. You don't have to be a language designer to contribute. You don't have to have an opinion. In fact, it's better if you don't have an opinion. You don't have to contribute code. Just contribute your experience. Just come back to us and say, I tried the code. This worked well. This didn't work well. What's going on? And that, that's the best thing that, for us, that's the most useful stuff that comes out of OpenJDK for us. Question in the back.
So you talked about indirection and recipes, but it sounds like in all cases across all VMs, the actual body of the lambda is going to become a private function of some type and surrounding class. Is that true?
Yeah, that's right. So the compiler lowers the method, the lambda body to a static method or an instance method. In a class, it's always private. It might be static, might be instance. Currently, if it's in an interface, the only thing interface methods can be is public. That kind of stinks. We're working on that. All right, last question, sir.
Will one method interfaces
Will single method interfaces work like lambdas when they're not capturing anything?
Yeah.
Yeah. Oh yeah. No problem. You can say runnable R equals empty parens arrow block. Worked great.
Yeah, but then if I have my own single method interface and I create my objects and pass them just like lambdas, will the JVM work out that maybe here we can do some tricks to lambda and make it 20 times better?
Oh, I see. Right. So if you created the object from an inner class, then it's an inner class. But whether you created it from a lambda or you created it from an inner class, from then on in its life forward, it's an instance of runnable, and the VM treats it as such. So the difference is how it gets created. But now IDEs may offer you hints of, hey, you can change this inner class to a lambda, and we'll do that for you. So.
Yeah, I was thinking more of inherited code that I can't change. Yeah, okay.
Yeah, that code will still work. All right. Thank you very much, everybody.